Welcome chemists to this episode of Bale's Chemistry. We're going to be looking at spotting isomerism in complexes. This is 2.5 transition metals with the AQA A-level chemistry syllabus, and it's on paper 1 of your final exams. So there are two types of isomerism present in transition metal complexes. The first one you'll have come across in your first year studies, and that's cis and trans isomerism. This exists where there's more than one type of ligand coordinately bonded to the metal ion and they sit at different positions relative to each other. The second one you might not have come across yet, and that's optical isomerism. It's called optical isomerism because of the effect that it has on polarized light. The two different molecules produced are non-superimposable on top of each other, which means they're essentially mirror images of each other. Looking at optical isomerism in more detail then, we need to have two molecules which are not superimposable on top of each other, which means they're essentially mirror images of each other. This can only happen with octahedral complexes where we have bidentate ligands. Each of the different isomers are called enantiomers. We can see on this diagram on the right where we have three bidentate ligands attached to the cobalt metal ion, we've got a very clear mirror image. Drawing these enantiomers can take a lot of practice, but what you must always make sure is that when you finish, you have two mirror images of each other. With this copper complex then, where we've got the bidentate ligand ethane diorate in an octahedral arrangement, we have both enantiomers here. Now we can check that they're a mirror image of each other by going through each ligand individually. We'll start off in the top left-hand corner where we can see this first ligand, and we can mirror that to the top right-hand corner of our second enantiomer. Moving around to look at the next ligand, which sits flat in the plane, we can see how that's mirrored across into our next enantiomer. And then the final ligand, the one that drops vertically down on the left-hand side of the first one, and then mirrored onto the right-hand side of the second one. This can be a good process to go through when you're checking that you've got two different enantiomers of your drawings in an exam. Cis and trans isomerism might already be quite familiar to you when you looked at the cis and trans isomerism around a carbon-carbon double bond. Cis and trans isomers are geometric isomers, and they're a type of stereoisomer. To see them in complexes, we need to have two different ligands present, and we need to check that when we've drawn them out, we can't rotate one enantiomer around to be the same as the other enantiomer. When it comes to identifying the cis isomer, we need to make sure that the same type of ligand is next to each other at a 90-degree angle. This is a little bit different to how you might have looked at it with the carbon-carbon double bond, but the degrees of the angle make it easy for us to see when we're looking at complexes. A trans isomer then is the same type of ligand opposite to each other, at 180 degrees. We see cis and trans isomerism in square planar complexes and in octahedral complexes. So we first look at cis-trans isomerism in an octahedral complex with this example of a copper ion with 2 chlorine ligands and 4 water ligands. In the enantiomer on the left-hand side, the cis enantiomer, we can see that the chlorine ligands are at 90 degrees to each other. In the trans enantiomer, the one on the right, we can see the chlorine ligands are at 180 degrees to each other. They're opposite each other. So when we look at isomerism in a square planar complex, you might remember this example we looked at in the shapes of cisplatin. Now cisplatin was an unusual one because it's got a platinum complex which tends to form that square planar shape. The cis enantiomer has its 2 chlorine groups at 90 degrees to each other. And then the trans enantiomer has 2 chlorine groups at 180 degrees to each other. They're opposite from each other. Hope you found this episode of Bale's Chemistry useful. It's quite a tricky one, so go back and make sure you understood all the little details. If you've enjoyed it, hit the thumbs up below, and don't forget to use the link on the screen to go back and watch all the videos on transition metals.